Today's lesson is on the inverse function and its properties. The inverse of a function is defined in your text as the reverse of the original function. The inverse of a function undoes what the original function has done. And as we will see, the way that we determine the inverse algebraically is to switch the x and y variables in the defining equation of the function. The fundamental idea behind an inverse is this: switch x and y, solve for y. So if it's the coordinates of a point, simply switch x and y. If it's an algebraic equation, switch x and y and then solve for y. But the fundamental idea is to switch x and y. So let's see a word problem example that would show us why it's important to know the inverse. Suppose the Lenarduzzi Paving Company charges $10 per square foot for installing interlocking paving stones plus a $50 delivery fee. And suppose Tom knows how much area he wants to cover and is curious as to the cost. So the Lenarduzzi Paving Company has a defined and set rule, and the customer comes to them knowing how much area he wants to cover. Okay? Well, what we could do then is create a function as follows. Simply let x be the area to be covered. Let f be a function of x, which gives us the cost of laying the tile for a given area. And from grade 9 math, we would see, therefore, that since our initial value is 50 and our rate of change is 10, our equation would be y equals 10x plus 50. But since we're putting it in function notation form, we can call it f at x equals 10x plus 50. We could make a table of values then. We could see that if Tom had 40 meters squared to cover, it would cost $450. But if he had 80 meters squared to cover, it would cost $850. We get these values by simply plugging in for x. Okay, so that part's probably fairly straightforward. But now, to get to the importance of inverses, suppose that Tom doesn't know the area that he wants to cover, but rather he knows how much he wants to pay, or he knows how much he can afford to pay. And so he's not calling the company saying, I want you to cover this much area, how much will it cost? He's calling the company saying, I know how much I can afford to pay, how much area can you cover? Well, that's the reverse of the previous situation. So suppose Tom knows how much he can afford to pay but wants to know how much area he can cover. This is the reverse of the previous situation. So in a sense we're switching x and y, and this is akin to finding the inverse. In other words, in the original situation, the independent variable represented the area and the dependent variable was the cost. But now we're going to make another table of values where the independent variable is the cost and the dependent variable is the area. So what we're actually going to do is switch the table of values from the original situation. So instead of having 40, 450 and 80, 850, etc., we're going to have 450, 40 and 850, 80, etc. So this would be our situation. And so we can go about using some grade 9 math principles and come up with the equation of the line representing all these points. Or we could take a little bit more of a inverse approach to this and simply do the following. We could go back to the equation that we had for the original function. We could switch x and y and solve for y, and that would be our inverse. So our equation that we had originally was f at x, or y, equals 10x plus 50. Well, now we're going to switch x and y, solve for y. So originally we had f at x equals 10x plus 50, so we say y equals 10x plus 50. After we switch x and y, we simply remove the y, put an x, remove the x, put a y. As simple as that. What we then want to do is solve for y. In other words, isolate the y. So, subtracting 50 from both sides gives us x minus 50 equals 10y, and dividing both sides by 10 gives us this equation for y. And it's nice to know the coefficient of x because that's the slope after all. So we can say 1/10 of x minus 50 over 10, or in other words 5, is equal to y. That's the inverse of the function. So we can say f inverse of x equals 1/10 x minus 5. Okay? So let's do an example. Find the inverse of the function defined by f at x equals 2 minus 5x, and we want to know, is the inverse a function? Well, we write down y equals 2 minus 5x, and then we switch x and y. So remove the y, put in an x, remove the x, put in a y. So now we have x equals 2 minus 5y. Now we want to isolate the y. So we say x minus 2 equals negative 5y, and divide both sides by negative 5. And now we can leave it as x minus 2 over negative 5, but it's good to know the coefficient of x and the constant term on the end, because this is our slope and this is our y-intercept. So we have negative 1/5 x plus 2/5 equals y. And so we can therefore say that f inverse of x is equal to negative 1/5 x plus 2/5. And this is a function. It's a straight line that is not vertical. It is a function. Okay? Now, what we're going to do in the next question is use the graph of each of the following functions to obtain the graph of the inverse, and then we're going to ask ourselves if the inverse is itself a function. So the first question is here. Looking at this, we want to, we see that we've got 6 discrete points, and that's our function consists of 6 points, and what we want to do is graph the inverse. Well, what that means is switch the x and y coordinates. So right here, this first point, this is the point negative 3, 1. So we can write that down here. Negative 3, 1. Well, if this is on the original function and we want to graph the inverse, remember what the fundamental idea of an inverse is. Switch x and y. Now in this case we don't have to solve for y, so we don't worry about that. We simply switch x and y. That's the fundamental idea of an inverse. So instead of negative 3, 1, we're going to make it 1, negative 3. We literally just took the x's and y's and reversed them. And we're going to graph that point. So negative 3, 1 is now 1, negative 3. And negative 2, 1 is now 1, negative 2. This point, negative 2, 1, became this point, 1, negative 2. And this point here, negative 1, 1, we switch x and y and it becomes 1, negative 1. We call that second point the image of the first point. So the image of negative 3, 1 is 1, negative 3. The image of negative 2, 1 is 1, negative 2. And the image of negative 1, 1 is 1, negative 1. Now this point up here is 0, 3. We switch the x and y, we get the image point of 3, 0. This point is 1, 0. Switch the x and y, we get the image point of 0, 1. And finally, we come over to here. This point is 4, negative 2. We switch the x and y and get negative 2, 4. And what we have now is the inverse of the function. So the black, 6 black points represent the original function, y equals f at x. The 6 red points represent the inverse of that function, y equals f inverse of x. Okay. Next, we have this function here, y equals g at x. And again, we remember the fundamental idea of an inverse is to switch x and y. If it's algebraic, we might solve for y, but this is not algebraic. We're simply going to switch x and y. So what we're going to do now is find 2 key points. We see that this point right here is the point 0, 3. That point right there is 0, 3, because each of these square grids represents 2 units. So if that's 0, 3, we want the image of that point, specifically, we want 3, 0. So we plot the point 3, 0. The image of this point is this point. Now, in the original function, we have 5, 0. Well, switching x and y, we see that the image of 5, 0 is 0, 5. And we come up to here, and we plot that point. Now, the original function is a straight line that contains both the points 0, 3 and 5, 0. Switching the x's and y's, we see that the image, or the reflection, or the inverse, will be a straight line containing the points 5, 0 and 0, 3. The inverse of a straight line is a straight line, and now we've graphed our inverse. Okay? Now, we can also do some word problem type questions. Looking at this example, we recall that a formula for converting Celsius to Fahrenheit is f at x equals 9/5 x plus 32. We're going to develop a formula for converting Fahrenheit to Celsius. Well, this is a lot like finding an inverse. We see y equals 9/5 x plus 32. But this y is the Fahrenheit temperature, and the x is the Celsius temperature. Well, I don't want to input Celsius to develop a Fahrenheit. I want to switch the x and y so I can input the Fahrenheit and develop the Celsius. That's the same as switching x and y, which is finding an inverse. So I take out the y, I put in an x, I take out the x, and I put in a y. And I now have x equals 9/5 y plus 32. And at this point I try to isolate the y. So I subtract 32 from both sides, and I get x minus 32 is 9/5 y. Then I can isolate the y if I multiply both sides by 5/9. And when I distribute the 5/9 in, I get 5/9 x minus 160 over 9 equals y. This is the inverse of the function f. And so I can say a formula for converting Fahrenheit to Celsius, instead of Celsius to Fahrenheit, is f inverse of x equals 5/9 x minus 160 over 9. There are a couple of notable points we want to mention. The inverse of a function is not necessarily itself a function. We saw that in this example right here. If you look only at the black dots, this clearly passes the vertical line test. However, if you look only at the red points, clearly it does not pass the vertical line test. The inverse of a function is not necessarily a function. If the original function is linear, then the inverse is also a linear function. And we see that here. We had a linear function. Well, the inverse is also a linear function. Now, one exception to that rule is if it's a horizontal line. If we were given a horizontal line to graph, we would get, imagine that that pen is the original function. And imagine that that is the function y equals 8. Well, if I want to change x's and y's, then my new function will become, my new inverse will become x equals 8. Well, if you view this on a graph, it would clearly fail the vertical line test, and it would not be a function. And we also see that if AB is a point on the graph of y equals f at x, then BA is a point on the graph of y equals f inverse of x. So by extension, the domain of f will correspond to the range of f inverse, and the range of f will correspond to the domain of f inverse.